Hey everyone! So here's our next unit. It is about genetic relationships. This is a little longer video, but it's hopefully going to be able to give you plenty of information so when we move on to the different things that we're going to be doing with it, which is going to involve quite a bit of calculations with different pedigrees and things like that. Hopefully, if you need to, you can come back to it and find the spot that you need to guide you through. In addition, I will be working on another example that should be able to help you guys walk through it and do these problems that we're going to be doing. But getting into it, just so you know, as far as genetic relationships go, they're really important to what we do in the livestock industry. It doesn't matter what species you're talking about, but it's important to be able to measure a genetic relationship. So it's basically measures of expected genetic similarities. So when we talk about these, it's really important that we understand how important genetic relationships are when we're selecting and mating livestock. Obviously, we want to avoid inbreeding quite a bit. I know that in previous units or whatever, we've talked about inbreeding and its effects, kind of touched on it. One thing that we do run into are genetic abnormalities that we see show up in these different breeds because of inbreeding in the past. There's different, like in the Line 1 Hereford breed, we actually saw some big issues because of inbreeding, specifically some dwarfism, things like that. In addition, maybe more recently in the Angus breed, in addition to probably just using bulls repeatedly, we do see some issues with inbreeding potentially in past generations that brought back up curly calf or waterhead or something like that. So it's really important when you're mating animals together to understand genetic relationships and how they play into that breeding. So we use pedigrees to show how animals are related to each other. These pedigrees, depending on how you keep track of your animals, a really simple way obviously is if they're registered, right? So if they're registered through a breed association, you can actually go on, you can see their pedigrees back numerous generations and really kind of evaluate how that'll impact it. In addition, if you maybe are in a commercial operation, you're not registering, lots of times, you can go back in your database and where you kept records and you can figure out these pedigrees if you want to figure out relationships between animals. What we do is we basically calculate the degree of the relationship by using these pedigrees. A lot of times, I don't have a picture here, I'll show you kind of what it looks like, but a lot of times these pedigrees are listed out in a simple way. We have, if we refer to the top side, referring to the sire, if referring to the bottom side, referring to the dam. So these pedigrees are really common in the way that they're expressed, but when we're talking about in this class, we actually use what we call a single arrow diagram to determine relationships. I'll show you it in this next couple slides. But basically, we take a pedigree and we convert it to an arrow diagram, and it's going to show you lines of descent. So it makes it a little easier to actually see like who came out of what and so on and so forth. So we actually might see an animal in a pedigree more than one time, but when we draw these arrow diagrams, they're actually drawn so the animal only appears once. So if you were to be looking at a regular pedigree, you would actually see, say the sire of the animal is also the sire of someone, a heifer or a cow a couple generations back, you'll just see it twice. Well, in an arrow diagram, we actually only see it once, and we use arrows, simple as that. So our male lines are shown using solid arrows, and the female lines are shown by using a broken or dotted arrow. So here's an example of a pedigree. So on the top, this is what we normally see, right? So you have animal X, you have the sire on the top side, dam on the bottom side, and then the paternal grandsire, maternal grandsire, etc., etc. In the arrow diagram, it looks pretty much the same on this example, right? So we have X, but as you see here, right, our sire is going to always have that solid line, while the dam always has the dotted line. So pretty simple arrow diagram. Here is another example. So we have this bull Argo. He is out of the bull Wee. Wee goes back to Jojo and Andule. Then Miss Lee 808 also goes back to Wee and Miss Lynn 33. But if you see in the bottom, obviously there's a big difference here. We know that we is a commonality between the top side and the bottom side. So instead of we being listed twice, he's simply listed once. But we show here, right, using this solid line, that he is both the sire of Argo and Miss Lee 808. So that's just an example to kind of simplify basically, you know, the pedigree into an arrow diagram. And it's really important to use these arrow diagrams in what we're going to be doing in the future. These are real examples of a Charolais bull, you know, Charolais cattle that I'm showing you right here. So moving on from there, so our pedigree is basically our first step. So in reality, you know, every time, one of the first steps we talk about is draw the pedigree as an arrow diagram. I will always have the pedigree converted into an arrow diagram for you guys whenever, you know, I present problems or homework or whatever, and you'll see that in the future, just so you know. But basically, after we have this pedigree and we evaluate the ancestors, there are some important things to remember. We use the arrow diagram to calculate the relationships, first of all. Second of all, direct ancestry. So when we say direct ancestry, that means the relation of animals and their descendants. So directly, okay? So parent to offspring, or, you know, grand offspring, but it's direct. Common ancestry is referring to animals that are not related by direct ancestry, but they might have one or more of the same ancestors in common, like a ways back. So when calculating these relationships, an arrow diagram that includes the common ancestors has to be drawn to include all the ancestors. Okay, so here's just another example of that. You know, we saw that bull a little bit earlier, but we put another one in here. So it shows that in this example here, right, that we is the sire to Argo, Miss Lee, and Catano. And then you see here that Catano goes back to Miss Lynn 33, while also Miss Lee 808 goes back. And so this is going to be the pedigree that I'm going to be using in an example coming up here in a few minutes of how we calculate the relationship. But just showing you again how the arrow diagram works even when we add more. You might have more complicated ones in the future as far as, you know, more animals. But yeah. So the measures of relationships. This is the measure of expected similarity between the genotypes of two relatives. And this is due to two things. So it's going to be genes that were transmitted from one to the other through direct ancestry, and or genes that were transmitted to both of them from the same ancestor or ancestors. We basically use this information to calculate what we call relationship coefficients and relationship covariance. These two things, these two calculations, are what we use to measure the degree of a relationship. That is something that we will be discussing in the following slides. Just so you know, when we start out here, I'm kind of talking to you on a grand scale, more the ideas behind these things, and then we'll get into the actual calculation and how we actually determine a relationship coefficient. So this first definition is really important. I cannot tell you in college when I took this class how many times I had to write it out, but it's just important to understand a relationship coefficient between two animals is the fraction of genes that are expected to be the same due to common and or direct ancestry that would have been different in two unrelated animals of the same breed. So a very kind of long explanation is basically saying what percentage between these two animals, what percentage of genes might they share? Okay, so that's what a relationship coefficient is. Now we do know that all animals of a breed are related to some extent, right? So if we look far enough back in their pedigrees, we will see similar ancestors. That's kind of a thing that's going to happen in certain breeds, especially depending on the size of the breed, you know, big or small. We're going to see probably similar ancestors. So we're not asking you, you know, you do not need to go back so many generations. Usually what we do is calculate relationships from either 4 or 5 generations. If you notice in the one that we did, I had on the few pages back, right? So it only goes back a couple generations. It really just depends on the problem. This is basically just giving you an idea. Now, if we do know that animals are related by many lines of descent, and we're seeing in those 4 or 5 generations a whole bunch of similar ancestors in animals, then that's when we might trace them back to the 6th or 7th generation. This is something that would be really important if you are seeing issues within a herd or within a breed, and you're seeing results of inbreeding negatively affecting that breed. So what we do is we can go back in farther generations and really be able to evaluate what those relationship coefficients are and hopefully put a stop or an end to that inbreeding and kind of make some changes. So mentioning inbreeding, I keep kind of going back to it, but we know that an animal is inbred if its parents are related to each other in some way. So relationship coefficient and relationship covariance, which we'll talk about a little bit more what the difference between those two are, but between two animals, it's going to be exactly the same if neither is inbred. So we know that if they're not inbred, there's not going to have, besides the fact that they might have, share a sire or something like that, they'll be exactly the same. Now, if an animal is inbred, the relationship covariance will be larger than the relationship coefficient. And just to kind of cast the future here, a relationship coefficient, like we just discussed, right, is going to be the fraction of genes that are similar. We use a relationship covariance, which we'll calculate and talk about. We use that covariance to find out the relationship coefficient. In addition to inbreeding coefficients and relationship covariances are going to give us our relationship coefficient. Hopefully that'll make a little bit more sense in just a few minutes. Okay, so continuing to talk a little bit about relationship coefficients. Parent and offspring relationships, this is going to be the simplest and most fundamental type of relationship, right? We can usually figure out exactly what's transmitting, kind of evaluate that, right? All other relationships are a combination of chains of parent and offspring relationships. So if we're talking about parent and offspring, and they're not inbred, we know that those relationship coefficient and the relationship covariance are going to be the same, right? And so between the parent and the offspring, it's going to be a half, right? So we know that the sire is going to give half their genes, and the dam is going to give half their genes to the offspring, and so they're going to have the similar percentage of genes just of their parents, and it's going to be a half. For the offspring and one of its parents, in the other half of their genes, so maybe in the offspring and like his sire, in the other half of the genes that offspring got, so maybe from his dam, the genes may or may not be alike. The same as two unrelated animals of the same breed might have the same genes because they're the same breed. And so what we're just kind of pointing out here is that the parent-offspring thing can be really simple, but whenever you start thinking about the genes that came from the other parent as compared, they might be the same or they might not be the same. And that is why we look at ancestors, to see what other genes could be similar just because they are related in some way, shape, or form. So we do talk a little bit about this going on, but we know that relationships of half-siblings are a simple extension of the parent-offspring relationship. So each of the two half-sibs receives half its genes from the parent they have in common. So for a specific gene that is one of the half-sibs received from a common parent, the probability that the other sibling receive the same gene from this parent is relatively a half as far as probability goes, because they might share the same sire, or they might share the same dam. On average, half-sibs have about a quarter of their genes in common due to common ancestry, if we don't see any inbreeding. So our parent and offspring relationships are not exact because we know that the offspring receives half of its genes from each parent. So it can, it's a 50% chance, but we know that half-sib relationship is an average or expected value. There's still quite a bit of variation there. So half-sibs, we actually see that they could have a fraction from 0 to half of their genes in common, depending on what genes each parent gave to those siblings. Now, full siblings have, on average, half of their genes in common due to having the same parents. And this is also definitely if there's been no inbreeding. So these are all kind of estimations. makes pretty much sense. Should at least that when we see siblings that there is still some variation. Full siblings obviously are going to have more genes in common, but this is also why that you might go out and you might see two calves that are both out of the same sire, okay? And they look nothing alike, or maybe all their weaning weights and all this stuff, you know, all their actual information varies quite a bit. Well, you have to realize that half sibs, yeah, they do possibly have fraction of genes that are similar, but there still is that probability, that possibility that basically their genes are, you know, from 0 to 50% the same. So you have to keep that in mind whenever you're talking about half siblings or even full siblings. There still is that probability that, you know, just on average maybe half are going to be similar. So inbreeding, like I mentioned before, an animal is inbred if its parents are related to each other. The genetic effect of inbreeding is increasing homozygosity, okay? So if a sire and a dam are related, we expect them to have genes in common, obviously. So when they're mated, there's a chance that they might both transmit that same gene to their offspring, and so that their offspring would be homozygous at that locus. So an animal also does obviously have the possibility of being homozygous at some of the gene pairs without inbreeding, but the possibility is just increased with inbreeding. We see this an issue, I'll talk about it again, you know, different deformities, different abnormalities, especially if you have, you know, an abnormality that is a recessive, like a homozygous recessive, and you have you're seeing that gene more and more throughout a generation or throughout different animals, and you breed two together that are maybe both heterozygous, and because of inbreeding they're heterozygous or something, and then in that offspring you do have a higher probability of them receiving the homozygous recessive gene and potentially expressing that abnormality or deficiency. So we know that it's a chance, like I said, at them being homozygous due to just actual, you know, chance, but we're just going to see a higher increase when we do inbreed. So the inbreeding coefficient of the animal is the fraction of its gene pairs that are expected to be homozygous that would normally be heterozygous in an average non-inbred animal. So that definition right there is an important one as well. So previous slides I talked about the relationship coefficient definition. This is another inbreeding coefficient. One thing you'll notice when we talk about these definitions, or I talk about them, is that I always say, you know, it's expected or on average, because this is also not an exact science. We are not taking genetic samples. We're using a pedigree to determine this. So just always remember that this is a good evaluation, a good expectation, but there always is a little bit of error there. So if we do see an animal inbred, obviously its descendants will be more closely related to the parents and to each other, and inbreeding continues. Okay, so here is a relationship coefficient. So we're finally getting into this. So what we're going to start talking about now is how do I calculate a relationship coefficient between two animals? So in order to get an estimate about two animals and their relationship coefficient, we use their pedigree, okay? So that pedigree we saw a few slides back of those different Charolais bulls and cows, we use that to figure out how many of their genes are potentially similar. And that is where we find our relationship coefficient. And you see in this first bullet point that is expressed as R sub XY right there. So what that's saying is RXY is saying this is the relationship coefficient between animals X and animals Y. So in the future, you're going to see me put maybe RAB or something like that. And so that would be the relationship coefficient between A and B, okay? So our relationship coefficient will always range between the numbers 0 and 1. So you'll probably get an answer like 0.64 or 0.21. What that is saying is this is the percentage of genes that, based on common or direct ancestry, this is the percent of genes that we would expect to be similar because of ancestry. Okay, so within our relationship coefficient, you see down here, this is the equation. So this is the equation you will need when we are calculating what these relationships are. The first aspect is going to be this covariance XY. Okay, so this is where I was talking about this relationship covariance. Okay, so we find, first thing we do is we're going to find that relationship covariance between two animals. We express this by just putting COV XY. So that's the relationship covariance between X and Y. Secondly, on the bottom here, you see this 1 plus fx times 1 plus fy, and you take the square root of it. So these are going to be the inbreeding coefficients. So respectively, right, we have f subscript x and f subscript y. That's going to be the inbreeding coefficients of x and y. So once we find out what these numbers are down here and we plug them in, this gives us our relationship coefficient. And so now we're going to talk about how to get to those numbers. Okay, so in that top, we have the relationship covariance of x and y. So how do we get that? So here's a whole bunch of steps. I actually break out each of these steps, so please don't worry. But if we want to be able to even get the relationship coefficient, our first step has to find those two animals' relationship covariances. I'll really quickly go through these because I'm going to flesh them out. But first of all, we use an arrow diagram from the pedigrees of the two animals, right? So we talk about those arrow diagrams. Animals should only be included once on there. Second of all, we make a list of the ancestors that would contribute to the relationship of X and Y. So basically, what are their common ancestors? What in that arrow diagram, what animals do X and Y have in common? It could be as simple as the fact that X and Y are out of the same sire, something like that. And you'll see an example here in just a second. If either one is a direct ancestor to the other, so like if X is the sire to Y, we also include that on the list of ancestors. So if any of the ancestors in the list are inbred, we calculate their inbreeding coefficients. I actually do this towards kind of the end, and I'll show you how I do that. But for each ancestor on the list, all independent paths of relationship between X and Y that originate from this ancestor should be put on the list. Basically, when we were calculating what this is and we're taking the pathways between X and Y, each pathway should begin with an X and end with a Y, and that ancestor should be somewhere in the middle. And it's going to make more sense in a second. The arrows change direction. No animal should appear more than once in the same pathway. Then we calculate their contribution and basically add up all the pathways to get their relationship covariance. And I'm going to go to the next slide so you guys can actually see what I'm talking about. Okay, so here is our arrow diagram for those same animals we talked about before. So what's the relationship coefficient between Argo and Catano? First of all, just so you know, we use letters whenever we're calculating these. You'll notice that soon. So I always, like, when I did these problems, I would kind of just pick a letter at the beginning. So Argo, I would say A, Catano is C, Miss Lee, you might, give her an M, give Miss Lynn 33 an L, we a W, Jojo a J, Andule an O. Pretty simple, but it's way simpler just to use the letters. So draw out the arrow diagram. Well, obviously it's already drawn out for you. So we determine first which ancestors contribute to the relationship of Argo and Catano. So in this pedigree, we know that those are both Wee and Miss Lynn 33. We know that Argo and Catano is not a direct ancestor of one or the other. So the only ancestors would be Wee. So you see Wee here. So obviously Argo and Catano were both out of Wee. So that is a common ancestor. And after that, we know that Miss Lynn is a common ancestor because she is the dam to Catano and she is also the grand dam to Argo. So Wee and Miss Lynn 33 are our two ancestors. From this pedigree, neither of the ancestors are inbred, so that avoids some issues there that we're calculating for later. They could be if we went back more generations, but you guys just take the arrow diagram that you are given. So after this is not meant to look overwhelming. It shouldn't be. It should be kind of a simple process. I say that, but I know it's going to take some getting used to. So the next one is, once we know what the common ancestors are, we establish the relationship paths between Argo and Catano, because those, remember, we're finding the relationship between A and C, okay? So this right here is basically just showing you how they are related. If you look over here, we have the ancestor, which is W, which is we, okay? And this is the pathway basically of how they are related, okay? So we have A goes to we and then back to Catano. And you notice that the arrows switch directions at the common ancestor. So basically arrows should switch directions right here as whatever letter is listed right here, okay? So we do all the pathways. So if W is a common ancestor, we know that they're connected by from Argo to we to Catano, but they're also, as you see here, connected from Argo to Miss Lee, 808, I gave her an L, to Miss Lynn, to we, and then back to Catano. So once again, sorry, I got Argo, Miss Lee, up to we, and then back to Catano. And those are the only two pathways between Argo and Catano through their ancestor we. Now we know that they do share, that Argo and Catano do share another ancestor, and that would be Miss Lynn. So she's listed right here. And then her pathway is going to go from Argo to Miss Lee, to Miss Lynn, and then to Catano. So what you notice here, right, is that all these pathways in this column should be from A to C. They should all start with A and end with C. And then we do notice that the arrows, when they switch direction, these letters here should correspond to this letter here. Okay, so stepping down here and looking at this chart, we have our ancestor in our first column. The inbreeding coefficient of the ancestor is right here. So it's basically 1 plus the inbreeding coefficient, which is expressed as f of A. Well, as we talked about, those two ancestors listed here, we and Miss Lynn, they are not inbred that we know of. So it's simply 1 plus 0. That's their inbreeding coefficient. Okay, so we have our pathways listed. We have all of them. So this column N is literally as simple as how many arrows did you do, okay? So 1, 2, that goes there. 1, 2, 3, that goes there, so on and so forth. So this next one, this is our formula to figure out what this is, and you're doing it by each row, okay? So in this case, it's simpler because 1 plus f of A is corresponding to whatever is in that column, that row's 1 plus f of A, and we know that that's just 1. So basically, when you don't have ancestors that are inbred, it makes it a lot simpler because all you do is you take half to the power of n. So it's going to be half squared, which is a quarter. In this one, it's half to the third power, an eighth, half to the third power, which is an eighth. And then when you do all that for all of the different pathways and the ancestor relations, we basically just add up this column right here. So a quarter plus an eighth plus an eighth is equal to a half. Now I will tell you right now, this last column, contribution squared, we will talk about it later, but for right now I just put it on there so I can refer back to it. We will talk about it later when we're discussing standard error. But right now we did basically our first 6 steps, okay? So, right, we did the sum of all the relationship pathways. So this is going to give us the relationship covariance of A and C. So, I'm referring back to that the formula, right? So now we have one part of the formula. So we're getting close. So now we have to determine inbreeding. And so when we talk about inbreeding, we have to calculate the inbreeding coefficient for both A and for C. And so these are the formulas over here, but basically it's fairly simple. An animal's inbreeding coefficient is equal to half the relationship covariance between an animal's sire and a dam. And we express them by f of A and f of C. So just laying it out here. So f of A, his inbreeding coefficient is equal to half of the covariance between W and L. Okay, so half between the covariance of we and Miss Lee, 808, because those are his two parents. Okay, and then the inbreeding coefficient for C is going to be half of the covariance between W and M. So in this case, if we examine the pedigree, we know for sure by just looking at Catano, okay? So when we look at the FFC, that his sire and his dam are not related by any way that we can see. So his inbreeding coefficient is going to be 0 because the relationship between W and M, the relationship covariance is 0. So that's shown right here. Now for Argo, his two parents are Wee and Miss Lee 808. And obviously they share a common ancestor because Argo's dam is also out of Argo's sire. So we have to calculate the covariance, the relationship covariance between W and L. So literally what we did on the last one, we just do the same thing between W and L. This one is fairly simple. We know that if we're looking at the relationship between W and L, the relationship is that W is L's sire. So we list the ancestor, W over here. We know that inbreeding for W is 0, right? So 1 plus 0. The pathway of relationship is pretty simple, right? So W is the sire of L. In this case, it's just one line because it's a parent and offspring relationship. So moving over here to N, the number is simply 1. And then we plug it into this formula, which is fairly simple because we don't have any inbreeding from the ancestor. So it's half to the first power, which is a half. So those are the only ways that they're related that we know by looking at this arrow diagram. So the covariance of W and L is simply a half. So in order to figure out what the inbreeding coefficient is for A, we take that covariance between his sire and his dam, which is a half, and we plug it in to this formula right here. So it's simply half times half the covariance between W and L, which is a half, and we get a quarter. So after doing this, we now know what the inbreeding coefficient is for A and the inbreeding coefficient is for C. So now that we've calculated all that we need, we can actually plug this into our relationship coefficient formula and we can get what their relationship coefficient is. So expressed here is the formula specific to A and C, Argo and Catano. So we put them together. So we know that from this right here, we calculated all the common ancestors and their pathways, and we came up with the contribution that they all three give, and we got a half. And this is our covariance of A and C. So we plug half in right up here because it's covariant, the relationship covariance of A and C. So we plug half in. Now on the bottom, we have 1 plus f of A and 1 plus f of C. So we know that f of A is the inbreeding coefficient of A, and f of C is the inbreeding coefficient of C, so Catano. And we just calculated those. So we know that inbreeding coefficient of A is a quarter, and for C it's 0. So we literally plug them in right here. So 1 plus a quarter equals 1, and then times 1 plus 0. Make sure to follow your steps of operation here. I like it when you guys, if you notice, I want you guys to keep these in fractions when you do them up to this point. And then whenever you do the final calculations, I'm fine with you converting them. So you see here that I did 1 plus a quarter times 1 plus 0. So it's going to be 1 1/4, and then a half is right here. So I went ahead and I obviously put it into decimal format. So make sure you add these together, right, and then multiply them before you take the square root, or you'll not get the correct answer. So I kind of show you guys that here, but I can't stress enough that order of operations is very important. So what we're getting here is we get a relationship coefficient for A and C that is 0.45. So what does that number mean? So basically, after completing all these steps and figuring out where Argo and Catano are related through ancestry, we know that they are expected to share about 45% of similar genes that would have been related between two unrelated animals in the same breed. So this is a pretty good thing to see. So say you're trying to use, use these animals on something, but this is basically showing you how to take two animals and to see how already similar they are. So is that high for you? I mean, It's quite a few genes that they could have in common, but now we know. So talking a little bit about the precision of relationship coefficients, obviously I can't stress it enough, relationship coefficients are estimated fractions of two animals' genes that are going to be the same due to common or direct ancestry or both. It's just an estimate. So we know that in reality, two animals' actual shared genes, they may differ some from what we calculate in a relationship coefficient, because we are not in there at the time of conception seeing which genes are coming from what or whatever. It's all an estimate. The chart here is basically showing you different, common relatives that we see, and basically what we would calculate the relationship coefficient as, and the range that we could see fractions or genes being in common due to ancestry. So, you have your parent offspring, the relationship coefficient is half. We actually don't see any variation because we know that happens. But in half sibs, a quarter, the variation can be from 0 to a half. Full sibs, half. You can see here, so there is some variation. So the farther away animals get, so grandparent, grand offsprings, we're going to see, a lower and the variation be different. 3/4 sibs, relationship coefficient is going to be 5/16, but the variation could be from 0 to 1. So there is quite a bit of variation there. So why do we talk about it? Why did I just tell you that relationship coefficients have some error to them? Well, relationship coefficients are very valuable if you're trying to mate two animals together and you have access to pedigrees. You can go in and you can figure out how much they have in common. There is going to be some variation, but it's still important to be able to see what they might have in common. So when we talk about the potential for error, we kind of go back to our statistics days. And so if you haven't taken statistics, it's going to be a very, very quick, very vague lesson in that area. So what we have left on that picture is, this is what we call our standard bell curve. So basically in the world of statistics, we see most data fall within this bell curve. So when we look at the bell curve, we have this area here, this first blue area, that's 68%. So if we're looking at like an average, so like an average number right here at the 50% mark, we actually expect 68% of all the data for whatever we're talking about to fall within what we call one standard error, one standard deviation. So 68% of all whatever is going to fall in this percentage, okay? Based on error, we would expect 95% to fall within this range, these two standard errors. So, and it says here, average performers, high performers, poor performers. So that's another way to kind of understand that, like, so you're talking about IQ, right? So you have an average IQ right here. We would expect 68% of the population to fall within basically this range, and we would have to find that range, which we're going to talk about in a second. And then you obviously see that the proportions get smaller the higher you go and the lower you go. And so this range that I'm talking about between 68% fall between 40 and 60 here. This range that we're discussing is called standard error. Okay, so standard error is a relationship coefficient is a more useful measure of the precision of the coefficient. So it's a way for us to evaluate how precise that number should be when evaluating similarity of genes. It's a sometimes simple measure we use in statistics that's basically a reflection of an accuracy. So standard error is going to basically give us this number above and a number below of whatever our average is, that is defining an interval where there's 68% probability that whatever these fractions of genes are, and this is how they actually have in common. So what does that mean for us? So it basically means that here's another step that we can do in determining basically the accuracy of the relationship coefficient we just talked about. So first of all, there are two different equations that we will use when establishing a standard error for these relationship coefficients. we express these by, S is R of X and Y. So basically we're taking that relationship coefficient we talked about, so R of X and Y, and putting it right here. So that's how we do that. But we have the parent to offspring and then the non-parent to offspring relationships. I don't need to get in a whole bunch about why a quarter is used, but it's obviously used in the different reasons when we talked about parent-offspring relationships, things like that. So we express the standard error by that. These are the two formulas we use. Pretty simple. If you're talking about a parent and offspring, use the first one. If it's anything else, use the second one. So basically for that contribution squared part, we use that last column that I basically said, hey, we'll talk about this column later when we were calculating relationship covariance. 2n, down there below, n is equal to the number of chromosome pairs for whatever species we are currently working with. I will always try to give that to you because it's just simpler that way. Okay, so this is basically how we calculate it. So this is just, I brought back up when we were calculating the relationship covariance between A and C. Okay, so this is where we're going to look at basically the standard error for that. So the relationship covariance for A and C, we calculated the contribution right to be 1/2. Well, this second column here is basically we take this number here and we square it and we put it right here, okay, for all the different pathways. And then we add them up. As you can see here, it says contribution squared. We already did that by doing this in the column. So we literally just take whatever total we have here and we just plug it in where it says contribution squared. We have to do that because if you were just to put a square root for this contribution by using the total, it doesn't work the same. You actually have to do the square root for each row and then add them up to get the total contribution squared. And then we plug that in. We know, and I'll give it to you, for cattle, they have 30 chromosome pairs, so you would plug that into this. So it says 2n, so it'd be 2 times 30. So as you can see here, I already did it to 60. Okay, so 30 is the n for the gene pairs. Okay, so 3/32 is on top here, and I converted that to the decimal form, and then 60 is on the bottom. So that would be equal to this square root, and then take the square root of that number, and you get 0.0395. In this case, I'm perfectly fine with you guys rounding, especially one like this, rounding to do 2 decimal points. So the standard error for the relationship coefficient between A and C is 0.04. So what do we do with that? So why do we calculate standard error? So we know that the relationship coefficient between Argo and Catano is equal to 0.45, so 45%, right? We calculated that previously. We know that that is how many genes we would expect them to share. So then we also calculated our standard error and we got 0.04. So when we use that standard error, we talk about the range. Basically, it gives us a more accurate estimate of the actual percentage of common genes between the two animals when we use those two numbers. So basically, we talk about the bell curve here. So in this case, we see this average right here, right? So this average would basically, we calculated the relationship coefficient as 0.45, right? For one standard error, that's basically where we use that number that we found. So it'd be like 0.45, we add the 0.04 that we got for the standard error, so it'd be 0.49, and then we minus on this side, and it'd be 0.41, okay? So now we're actually applying the numbers that we use to this actual bell curve, and we basically are seeing that in that first standard error, 68% chance that it lies between 0.41 and 0.49. Okay? So that's expressed here. So that standard error, basically when you take that standard error, you subtract 0.04 off, you add 0.04 on, and you get these two numbers. So the takeaway here is that there's basically a 68% probability that Argo and Catano share between 41 and 49% of similar genes based on what their ancestry is. So that is why we do the standard error on top of relationship coefficients. I will not always have you do the standard error, but I think it's important for you guys to understand that in any kind of formula and evaluation of different numbers, there's going to be some kind of error. And especially in our industry, we're going to see this also a lot when we talk about EPDs in the future. A standard error and accuracy and being able to measure it accurately is super important. So in summary, just kind of going back real quick, this whole thing is really important because we need to be able to establish relationships between animals if they're related. We know that animals inbred because its parents are related. We know that we can, determine a fraction of its gene pairs that might be homozygous due to inbreeding. Most of this was all about relationship coefficients and, establishing them based on two animals and how many genes are expected to be the same. And then the standard error is going to be the relationship coefficient, of a relationship coefficient is basically a measure of precision. Once again, all this is all an estimate, and so that's really important to remember moving forward. Here's just another little summary that I do for you guys. Now, this is really specifically talking about relationship coefficients. We just touched on standard error, so I'm not going to beat that into your head so much because we're not going to be doing it quite as often. It's really important that you guys understand how we come up with relationship coefficients and why it's important. So at the top here, I kind of summarized it. R of X and Y is the relationship coefficient between animal X and Y. It has to range between 0 and 1, and here is the formula that we use, okay? Covariance, the relationship covariance between X and Y is listed here, and we need that obviously to calculate our relationship coefficients. It can actually range between 0 and 2. That's just because of different inbreeding, okay? So if we add an inbreeding, that actually ups our total. But so basically the first thing we do is we create this chart thing right here, okay? So this chart thing is going to be a way for you to list out the common ancestors between X and Y and determine their pathway, okay? So A would be the common ancestor. 1 plus f of X is going to be that ancestor's inbreeding, so it would be 1 plus whatever the inbreeding coefficient is for them. This pathway, we know that we use arrows to connect the two together. So in this case, we're referring to X and Y. So must begin with X, end with Y. The arrows are going to change direction of the common ancestor, and we do not repeat a letter in our pathways. If a letter is repeated, you know you did something wrong. N is simply the number of arrows that was in that pathway that you just wrote down. Contribution here is listed as half to the n power, which that's the power you get, times 1 plus f of X, which is from this column here if there's anything in there besides 1. And then contribution squared is this column squared, and we would use that later for standard error. And then lastly, the last thing you need to calculate relationship coefficients is going to be f of X and f of Y. So just one example down here, f of X is equal to the inbreeding coefficient of X, which would be half of the relationship covariance of X's sire and dam. I don't have their sire and dam listed here, so you can refer back to the previous slide if you want to. That is relationship coefficients in a nutshell. This is a big unit and a lot of information. It's super important. I'm going to try to put up numerous examples, and then I'm going to go ahead and probably assign maybe like one problem or something and see how you guys do with it and see what we need to work on. And then we can go from there, and I'll probably assign some more homeworks associated with this. Please ask me any questions. I know this was a long video. I hope it was a lot of good information. It would be just like we were in a lecture, so that's like your one this week. So thank you guys for everything. Please let me know if you have any questions or concerns, and please be checking your emails. Thank you.